Introductory circuit analysis using an unconventional, intuitive approach. Session 5.
Greetings viewers.
Here we emphasize how things really work intuitively rather than blindly use mathematical methods. No mathematical background in differential equations or Laplace transform is necessary. All we need is basic calculus and working knowledge with spreadsheets such as Microsoft Excel, and familiarity with Kirchhoff's current and voltage laws, that is KCL and KVL. Please hit the like button and subscribe to our channel to encourage us to launch more videos like this. In the earlier sessions 1 through 4, we discussed linear RC and RL circuits, and a nonlinear circuit as well. Without using sophisticated mathematical techniques, we tackled both linear and nonlinear circuits quantitatively. You are encouraged to review the material. In the 5th session, we are going to discuss resistor-inductor-capacitor circuits. The schematic of the series resistor-capacitor-inductor circuit is shown. We will create our spreadsheet next. We will enter inductance in nanohenries, capacitance in picofarads, resistance in ohms, and time step in nanoseconds. Capacitance in picofarads. Inductance in nanohenries. Resistance in ohms. Current in amperes in column E. Voltage across resistor in column F. Voltage across capacitor in column G. Voltage across inductor in column H. Rate of change of current in column I. Now let us set the initial conditions. There are two initial conditions possible with this circuit, the inductor current, and the capacitor voltage. The initial capacitor voltage is shown. The initial inductor current is shown. Let us consider the instant before the switch is closed. The initial inductor current is shown. The initial capacitor voltage is shown. The other parameters, namely the resistor voltage, inductor voltage, and rate of change of current, are 0. Let us consider the instant immediately after closing the switch. Current through inductor cannot change instantaneously, and therefore will be same as before closing the switch, that is, the initial condition. Voltage across resistor calculated as shown. Voltage across capacitor cannot change instantaneously, and therefore same as that before closing the switch, that is the initial condition. Voltage across inductor determined using KVL as shown. Rate of change of current calculated as shown. Current at next instant of time calculated as shown. Formula same as previous instant of time. Voltage across capacitor is calculated based on charge gained or lost in time delta t. Formula is same as in previous instant of time. Formula same as in previous instant of time. Let us now discuss the method for selecting the time step. First we introduce a dimensionless parameter called damping, described by the equation shown. As we will see, the shape of the response is altered dramatically depending on whether delta is greater than, or less than 1. For damping greater than or equal to 1, we could use 2 times L over R as the effective time constant. The time step must be at least an order of magnitude smaller than this effective time constant. As you notice, there is no capacitance in the equation for effective time constant. There is a reason behind, and the details can be provided to those interested. The effective time constant, 2 times L over R, in nanoseconds is calculated as shown. Therefore, time step is taken at least 10 times smaller than the effective time constant. We will start our first exercise with LCR circuit with the schematic shown. This helps us in conceptualizing how the initial condition for capacitor voltage can be implemented. The changeover switch changes over from position 1 to position 2 at t equals 0. Therefore, voltage from the battery becomes the initial condition for the capacitor voltage. If we set the input voltage to 0, we should observe the behavior of the capacitor discharging through the inductor and resistor. As in earlier sessions, time sequence is in column A. As in earlier sessions, input voltage is in column B. We set input voltage to 0 to observe the discharge by the capacitor. The formulas for various voltages, current, and rate of change of current have been established earlier. Therefore we can determine the above parameters as a function of time by simply scrolling the mouse down. Voltage across the capacitor is plotted using red triangles and observed to decrease due to the capacitor discharging through the inductor and resistor. The current, plotted using blue squares, starts from 0, and its magnitude increases with time. Let us discuss some results now. The capacitor voltage is plotted in red, and the current in blue. The current is negative due to the sign convention followed in the schematic earlier. It is observed the magnitude of the current starts from 0, keeps increasing and then starts decreasing. For comparison, the characteristics of an RC circuit with the same resistance and capacitance values is shown by the dotted line. For the RC circuit, current is maximum at t equals 0 plus, and monotonically decreases thereafter. For the RLC circuit, the current must start according to the initial inductor current, which is 0 here. It then takes some time to reach the equivalent RC circuit value, and then closely follows the latter. Current obtained using the present method is plotted in blue. And current obtained using analytic method is plotted in green. Excellent agreement is seen in general except for the initial few points required for convergence. Keeping L and C the same, let us now change the value of R from 500 to 25 ohms, that changes damping from 2.5 to 0.125. Overlaid plots of the current for the two resistance values are shown. As we saw earlier, the current for R equals 500 ohm shows no oscillatory behavior, it changes magnitude, but always flows in the same direction. However, current for R equals 25 ohm shows a strong oscillatory behavior, swinging between positive and negative values. Let us plot the capacitor voltage, in red, overlaid on the current, in blue, to get a better insight. We observe that a maximum magnitude in current corresponds to approximately 0 capacitor voltage. In the preceding example, that is for R equals 25 ohms corresponding to a damping of 0.125, we maintained the time step same as the scenario for R equals 500 ohms causing no problem. However, the effective time constant for damping less than 1 can be taken as the expression shown. Therefore, we could have relaxed the time step to a larger value to simplify calculations. Let us plot the capacitor voltage, in red, overlaid on the current, in blue, once more, but over a longer time duration. We observe that a maximum magnitude in current corresponds to 0 capacitor voltage. And, a maximum magnitude in capacitor voltage corresponds to 0 current. This is the so-called quadrature relationship between the two. Current obtained using the present method is plotted in blue. And Current obtained using analytic method is plotted in green. Excellent agreement is observed, as it was for the high damping case discussed earlier. Now let us try to acquire a better insight into the physical mechanism behind the oscillatory behavior. For that, let us assume for the moment the circuit to be lossless, that is, R equals 0 implying no damping. The plot displays the capacitor voltage in red, inductor voltage in green, and the current in blue. It is obvious that inductor and capacitor voltages must add up to 0 to satisfy KVL, and therefore appear to be in antiphase. At t equals 0 plus, capacitor is charged to maximum voltage and no current has started flowing. Electric field in capacitor is strongest as depicted by red color. The capacitor starts discharging through the inductor till it reaches 0 voltage. There is no more electric field in the capacitor, and all the electric energy in capacitor has been converted to magnetic energy due to current flowing in the inductor. Since the voltage across the ideal inductor is 0, the rate of change of current is 0 too. This is manifested by zero slope in the current, that is, the blue curve. The rate of change of current is 0 and therefore current through the inductor must keep flowing in the same direction, and has no option but to charge the capacitor. However, it deposits positive charge on the bottom plate and therefore the voltage across the capacitor becomes negative. Therefore, at an instant immediately after the previous instant of time, the capacitor develops a small negative voltage, and a weak electric field, as shown by the blue color. Thus we see how the capacitor voltage changes sign. The magnetic energy in the inductor keeps charging the capacitor till inductor current becomes 0, and maximum voltage is reached in capacitor with strong electric field, shown by the red color, but obviously, with a reversed polarity. After that, the process repeats itself. We just discussed qualitatively how the energy gets converted between electric and magnetic forms repeatedly. Quantitatively, the energies are described by the equations 1 and 2. Using the equations 1 and 2, the peak current can be expressed in terms of the initial voltage resulting equation 3. You are encouraged to calculate peak current using equation 3, and compare with the value obtained from the spreadsheet. The instantaneous electric and magnetic energies are plotted using red and green colors respectively. For comparison, the earlier plot of capacitor voltage and current is also shown. As this is a lossless system, the total energy stays constant and merely transforms between electric and magnetic forms repeatedly. You are encouraged to make a plot of instantaneous energy when R is finite but damping is less than 1. You are encouraged to investigate the following. If damping is reduced from 2.5 gradually by changing the resistance value, how the current waveform changes, especially for damping values around unity? How does the total duration of oscillatory behavior changes in the above experiment? How the time period, or frequency, of oscillations varies with L and C values? How does the current waveform look if R is less than 0? Is it possible to generate negative resistance? So far we have studied the behavior of the circuit with respect to initial charge stored in the capacitor. For this reason no stimulus has been applied. Now let us consider the behavior of the circuit to a step function stimulus of 1 volt. Initial capacitor voltage and inductor current are assumed 0. We expect the capacitor to be charged to input stimulus of 1 volt, which we do observe in all 4 plots. For damping values of 2.5 and 1, the steady state is reached without oscillations. However, for damping values less than 1, the steady state is reached after oscillations or ringing as they are called. This phenomenon might create a problem with digital circuits where we would like the pulses to be as clean as possible. This ringing may result from parasitic, that is undesired inductance and capacitance present in the circuit inadvertently. Now let us consider sinusoidal stimulus. The natural frequency of the circuit, denoted f0 and described by the equation shown, is 15.92 MHz in this scenario. Let us find how the circuit reacts to sinusoidal stimuli at different frequencies. Let us first use 14.92 MHz as the frequency of the sinusoidal stimulus, that is, 1 MHz less than the natural frequency of the circuit. The stimulus has an amplitude of 1 volt, shown by the green plot. Capacitor voltage is shown by the red plot. After initial transients have died down, the steady-state amplitude is around 7 volts, considerably larger than the stimulus. Next we use 15.92 MHz as the frequency of the stimulus. Here the steady-state amplitude across the capacitor is even larger, around 20 volts. Next, we use 16.92 MHz as the frequency of the sinusoidal stimulus, that is, 1 MHz higher than the natural frequency of the circuit. After initial transients have died down, the steady-state amplitude is around 7 volts, similar to the 14.92 MHz scenario. You are encouraged to try out this behavior at frequencies further away from the natural frequency, say for 10 and 20 MHz. Now let us discuss the energy exchange for the three scenarios discussed. At 14.92 MHz, electric energy, that is, in the capacitor, is greater than the magnetic energy, that is, in the inductor. At 15.92 MHz, electric energy, that is, in the capacitor, is equal to the magnetic energy, that is, in the inductor. This condition is called resonance. Notice that the scale for the plot in this scenario is almost an order of magnitude higher than the previous. Finally, at 16.92 MHz, electric energy, that is, in the capacitor, is less than the magnetic energy, that is, in the inductor. Now we discuss the frequency domain behavior of the series RLC circuit. Frequency domain behavior is the steady-state response for sinusoidal input, as introduced in session 2. We introduce a parameter called Q or quality factor, that is inversely proportional to damping. The capacitor voltage as a function of frequency can be expressed in terms of quality factor and natural frequency as shown in the equation. At resonance, the magnitude of the voltage across the capacitor, and also the inductor, is Q times the input voltage. This is shown in the plot where the peak voltage is 20 times the input, the Q in the example being 20. The magnitude of the capacitor voltage as a function of frequency is plotted in blue using the analytic formula just described. The red cross marks denote the frequency domain response as calculated by our present method. We see good agreement between the two methods in general. To determine the steady state accurately, one need to have large number of time points for the transients to die down. Also, one needs sufficiently small time steps as to reduce error due to undersampling. We just discussed an example of a bandpass circuit. This type of circuit allows a small band of frequencies while suppressing others. You are encouraged to try the following as described. The sharpness of resonance can be quantified in terms of the bandwidth. We determine 2 points on either side of the peak frequency where the magnitude is 0.707 times the peak value. The difference between these two frequencies is the bandwidth. The bandwidth is related to the natural frequency and quality factor by the equation shown. For our example, the bandwidth is thus calculated to be 0.8 MHz. You are encouraged to verify it, and also, investigate how bandwidth changes with Q factor. This concludes the video on RLC circuits. Thanks for a patient hearing. We plan to come up with more exciting videos in the fascinating world of electronics and electrical engineering. Your feedback is very important. Please feel free to comment or email if you have questions, suggestions, or need supplementary materials. Till then, stay safe, and stay tuned.